So this video is about logarithms, which for whatever reason seems to get a really bad rap among students. I've run across a lot of people who don't like logarithms, or said, I understood everything until logarithms. Don't let that be you. Of course, if you have questions after this video, please ask me. I'm happy to field any questions about this sort of thing. But logarithms are really, really, really useful. In fact, logarithms really were the sort of thing that helped understand how to build computing devices before people built computers. I'll show you that in a moment. But what are logarithms? Well, they sound kind of scary, but they're not so scary. Logarithms are just exponents in reverse. Logarithms are just exponents in reverse. What do I mean? Well, suppose someone asked you how to solve this. Someone asked you how to solve 2x equals 32. What do you do? Well, like this is the sort of thing you say, well, I do the same thing to both sides. Maybe I divide both sides by 2, like so, and I get x is equal to 60. Or maybe they say I multiply both sides by 1/2. That's the same thing. No problem there. So this is pretty easy, right? I can solve equations like that. But now what if instead of someone asked 2 times x equals 32, someone said, what power of 2 to the x gives you 32? Now it's not so easy. But now, let's see here. This is something we can do probably, like 2 to the 0, that's 1. 2 to the 1, that's 2. 2 to the 2, that's 4. 2 to the 3, that's 8. 2 to the 4, that's 16. 2 to the 5, that's 32. What did I do? I used a geometric series, or a geometric sequence rather, 2 to the x, and just sort of worked up until I got the answer I was looking for. So that tells me that x is equal to 5. Okay, now you don't want to have to do this if, like, someone says, you know, well, I don't know, for x, I don't want to have to like do this a whole bunch of times. This is not so bad. This is 16, but in any event, x equals 16 in this case, but in any event, I don't want to have to like do out this sequence. That would be sort of pain in the neck. So what mathematicians did, being fundamentally lazy creatures, is we tabulated the results. We wrote them down somewhere, wrote a table of logarithms. What is a table of logarithms? Well, so basically it's a cheat sheet, list of answers to this kind of problem. We did it for various bases. We wrote them all down. So what a logarithm is it's a way to solve this problem. So here, I'm going to change some notation. We're going to write, we're going to say something here, and then we're going to write it out. The way we can say this is that in this problem, x is the base 2 logarithm of 32. And of course it's 5 is the base 2 logarithm of 32. Okay, what that means is that 5 is the solution to this equation. So this is a direct translation of 5 is the solution to 2 to the x equals 32. Now this suggests that you can do a cut and paste kind of way of writing a sentence like this and a sentence like this. Okay, and I said there's some notation. The notation is pretty straightforward. The notation is 5 is log base 2 of 32. So that little 2 there, that's the base. This is the thing you are logarithming. And this is the answer. So you can read this as being the same thing as saying, well, I'm going to solve this equation to find out the answer is 5. That's what this is saying. Well, let me write it out a little more succinctly. So if I have b to the n equals a, that equation, and I'm trying to solve for n, our job is solve for n. Well, the answer that you're going to get, that is the same thing as saying now that n equals the log base b of a. And of course, this sort of thing is a little hard to see where everyone went, so let me color code it. Here's your n, there's your n. Here's your b, here's your b. And finally, here's your a, here's your a. So these two things are actually the same equation. They mean the same thing. That this one here is just written in a different way. It's written to expose the exponent. To expose the exponent so that it's easier to work with. Okay, so we can solve lots of problems like this. We can solve lots of problems with logarithms. For instance, we can solve, 10 to the x is, let's say 10 to the x is 15. Well, what x does it have to be? Well, see, if you started writing down a sequence, that geometric sequence described by the functional equation 10 to the x, what do we get? Well, let's see, 10 to the 0, that's 1, 10 to the 1, that's 10, 10 to the 2, that's 10 times 10, that's 100. Uh-oh, wait. Here, we're smaller than 50, we're too small, and then suddenly we're too big. That whatever x ought to be to solve this equation, it ought to be in between here. So x, the x value is somewhere in there. So 10 to the x is somewhere inside the here. Is in here. Another way to say this is that x has to be between 1 and 2 somehow. So x is between 1 and 2. Now what is x? X is this base 10 logarithm of 15. So 1 is less than the base 10 logarithm of 15. I don't know a heck of a lot else about what this logarithm of 15 is. It's sort of hard to figure out what that number is. I mean, like, these are the easy ones to do. Well, this is why that table of logarithms was invented. It makes it much easier. You look up that table. This is what your calculator now does. It has that table of logarithms built in. You can type it in. I don't exactly know what it is offhand, but that's pretty good. So you can take any number that you want to find the logarithm of and start writing out that sequence. You can see what is definitely too small and definitely too big. And it'll give you an idea of what that logarithm is. It doesn't tell you the exact value. You can approximate it this way. Now, logarithms are useful for another reason. Remember I said that what people did when they found out about logarithms is they started tabulating big tables of logarithms. So they didn't have to solve equations like this every time they were run across. But there's a problem with that. Like I have to do this for tens, for the base 10. I have to do them for 2s, 3s, 4s, and what turns out to be really important in more sophisticated contexts are things called base E. And E is some crazy number that's like 2.71828, and there's a whole bunch of other stuff, a whole bunch of other numbers. So it's some decimal number. Gosh, I don't want to tabulate all of these. This seems really obnoxious. And so there's something very nice about logarithms is that they let you change the base of an exponent. See, this equation here, maybe I shouldn't erase it, but this equation here tells us something. Sort of fundamental defining principle of logarithms is really handy. So suppose, for instance, I have 2 to the 3, that's 8. I know what that is. Well, let's say I don't want it to be 2 to the 3 being 8. I want to know some power of 10. I want 10 to the x equals 8. I want to find, so we know this. And we want x. I want to know this. That x. Well, one thing you can do is you can try to convert this problem into this problem. You say, how do you do that? That seems kind of dubious. Well, it's sort of like this. You say, well, maybe I could write this 10 in terms of this 2. Like, I really want to use my exponent rules. 2 to the something. to the x is going to be 8. So here what I'm doing is I'm saying I really want this thing to be a power of 2 to the something. Okay. But wait, this exponent rule thing lets me do that, right? And I now have sort of transferred the problem into solving 2 to the n is equal to 10. That's another logarithm problem. Maybe I've got the table of 2 logarithms around. So we have the known table of base 2 logs. That's what we're going to do here. I want me to use my base 2 logs to find this guy, log base 2 of 10. Okay, so that says that here, this is 2 log base 2 of 10 to the x equals 8. Now I'm going to use my exponent rules. My exponent rules say this is really 2 to the x, log base 2 of 10. Switch the order of the x into log 10 just so that it's kind of clear what I'm logging and what I'm not logging. Of course, this is supposed to equal 8. But wait a moment, 2 to the something equals 8. I know what that is. 2 to the 3 equals 8. So that means this thing here has to be 3. So 3 is x times log 2, 10. So what's x? It's 3 divided by log base. So what this let me do, what happened here? What happened? It's sort of a magic trick. I was able to find out this power of x, or this power of 10 rather, by using the fact that I was able to find powers of 2 appropriately. So I was able to transfer the problem. Once you've got logarithms for any base, you actually get them for any other base. Hey, that's wicked handy. Let me write this down as a general principle. So that if I have a logarithm based A of based perhaps B of A, and I really don't want it to be log based B. I want it to be log based C. I really want to work with log based C. I can just do this. So I can change bases of logarithms. This is called the change of base formula. So I can write down in a very simple way everything in terms of one particular favorite set of logarithms. Now typically people like to use base 10 because like 10 to this stuff is something that we're pretty good with. Unless you're really into computers, in which case it's like all base 2, or if you're like a physicist or an engineer or something that is usually based E, well, that's a funny number E again, in which case they call them natural logarithms. Now, at this point they probably seem rather foul and unnatural, but there are good reasons for picking natural logarithms. But in any event, what's beneficial about this is now, let's solve that problem that we had just on the board a moment ago. We wanted to find 10 to the x is equal to 8, but we only say had the log 2's floating around. The answer to this problem is log based 10 of 8. We don't know it. So let's write it out with the log base 2's that we know. Log base 2, 10. Just as we had found. In log base 2 of 8, this is the answer to the question, what power of 2, 2 to the what, is equal to 8? And that was the 3. And this is just the answer we had a few minutes ago. So this change of base formula is very handy. So that's something that lets you manipulate the solutions to these kind of equations in a very convenient fashion. Now, why were logarithms really so pivotal? Logarithms were really pivotal because they allow you to multiply really big numbers by hand once you have the logarithm table. I mean, if you're able to multiply large numbers by hand, by computer, that's great. If you have the logarithm table, that's great. But suppose you don't have the computer, but you do have a log table. And these were something that were compiled at great expense in the 1700s, for instance, in the 1800s. Well, what that lets you do is it lets you multiply really big numbers. Let me show you why. Let's say you want to multiply a big number x and a big number y. These are both big, big. Okay, those big unfortunate numbers. Now, what you do is, let's say we have a table of base 10 logarithms. So how do we multiply these? How do we multiply when we have a table of base 10 logs? Well, what do? Well, base 10 logs. You ask the question this. 10 to the p is equal to x. Find me the p that gives me 10 to the p is x. And you ask, find me the q that 10 to the q is y. Okay, your base 10 logarithms can do this for you, and that's what the table's for. So you look at your table and you find out the answer. Log base 10 of x, that's p. And q is the log base 10 of y. Okay, so I've done that. Now why would I do this? Well, that tells me what these exponents are. So let's go over here and see what does that let me do. Well, that says x is 10 to the p, right? 10 to the p times 10 to the q. Oh, wait, I have an exponent rule, don't I? My exponents rules, let me write this as 10 to the p plus q. Hey, I just did that multiplication as an addition. Adding those two numbers, these p and q, they're not particularly big numbers. Furthermore, adding is really something that's pretty easy. I mean, even computers can do addition. Gosh, that's not so hard. And then coming back here, writing back to the base 10, sort of 10 to the something. That's also something pretty easy. And it's something else that if you use your logarithm table in reverse, you can do pretty easily. So in particular, this expression, 10 to the log 10 of x plus log 10 of y, that's pretty easy to do. So we've turned multiplication into addition. That's why they're really handy. Now, log tables were great for that purpose, and that's what was the scientific standard of high-powered computation. Now, more recently, not very recently, but more recently, sort of, perhaps your parents, not your parents' generation, but perhaps a little bit before that, thinking here 1960s or so, those ideas here were still being used. Computers were not in wide usage. Computers were big room-filling behemoths. They're pretty awesome, to be honest, although they took a lot of electricity. Probably bad for the environment. But there weren't that many of them, certainly. But how did you manipulate these things? Well, you didn't want to carry around tables of logarithms if you didn't have to. But if you were an engineer and were building things, you'd sometimes have to multiply big numbers. How would you do it? Well, you'd use something called a slide rule, and I happen to have one. In fact, a colleague of mine lent me this. And here is a slide rule, which is a big logarithmic machine. And it slides, which makes it all the more fun to use. But here's the idea. What's printed on here are a bunch of numbers. You know, on one end there's the number 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And this one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Right, there it is. It probably doesn't fit on the screen. But that's all right. The idea here is that notice the spacing between one, from this spot here, and the 1, here, there's the 1 and the 2, is, well, that's a lot longer than the 2 and the 3, 3 to the 4, that gets kind of squished on the other end. Why is that? Well, they're actually printed on a logarithmic scale. So when I add lengths with this ruler, they're set up so that they're adding these guys here, and I multiply. So check it out. So let's say I want to multiply 2 times 3 to get 6. What I do is I slide this little marker here, the 1, over top the 2. So this is the slide rule sliding feature. So I've slided, it's a little hard to see perhaps, bring it up here. I'm sliding the 1 on top of the 2. And so that's the length of, that's the logarithm of 2 as it happens. And then here's the logarithm of 2, I'm adding them together, and it reads out 4. Hey, cool. And if I go read it out to log 3, that's 6, 4 is 8, etc. So this is, in fact, a way to multiply numbers, sort of using geometry and logarithms. And this sort of tool was the tool that people would use to manipulate these sort of numbers fairly quickly. It's not necessarily very accurate, but it does the job. And this is the sort of thing that was used for computations live when people needed to do them quickly before they had calculators on hand, electronic calculators. They came about in 1978 or so. That was the invention of the microprocessor, which we now very much rely on. In any event, this sort of tool makes use of these laws.